by now we know what magnetic flux lines are. We know that magnetic flux lines are these things that are induced in a bar magnet. And I'm always going to draw them in blue. And these magnetic flux lines go around in the space around the magnet, and they sort of concentrate near the poles of the magnet. And if I have a smaller bar magnet, then I actually do have a smaller amount of like a count of magnetic flux lines. But then if I have a larger bar magnet made out of the same material, then I'm literally going to have more magnetic flux lines. And these are continuous lines that run all the way through and obey our, 7 principles of magnetism. Don't touch like what I just made them look like they're touching, etc. They go all the way through. They have a direction out of north and into south, etc. So, but here's this one would have larger magnetic flux, just if it's made out of the same material. So let's look at these two things, and I'm going to say, well, let's actually, you know what? I could make it. Let's actually. I think I'm gonna change my mind, and I'm gonna make these out of two different materials, two ferromagnetic materials, and they're going to be a similar size magnet. And this one's going to be very, very, very intense with its magnetism, when lots and lots and lots of flux lines. And that's very, very messy. But I'm going to say larger flux. It's just a more magnetic. For whatever reason. That could be the type of material. That could be like it could be more magnetic in the case of an electromagnet because you put more more current through it. I'm just going to say here's some not very magnetic situation, and here's a more magnetic situation so that I can compare the two. And what magnetic flux density is it is literally, the word density just means quantity within a space, right? The word density, population density, means number of people in a certain amount of space. Mass density means the amount of kilograms in a meter squared, in a meter cubed. So the English word density means like quantity in a space. And we already have a definition of quantity of magnetism, and that is called magnetic flux. And that is measured in Webers. And it is, by definition, a count of 10 to the 8 lines of flux. All right, so 10 to the 8 of these flux lines. I don't see 10 to the 8 flux lines here or here. There are less than 10 to the 8, less than 10 to the 8. Right? So, but it's a quantity in a space. So if I take those lines of flux and I put them in a space, and the space I'm going to put them in is going to be normalized. And normalizing means to divide by something so that we're all looking at the same thing. So again, an English word to normalize. What I'm going to do is I'm going to take a little plane of this material, and I'm going to take a little plane of this material, and I'm going to use the same size plane. So this is the same size plane. And if I take this plane out, and I take this plane out, then, and I lay it flat, I'm laying these planes flat, they are the same size. Now, I had a very magnetic material, and then I had a not very magnetic material. So when I take those out, I know that the magnetism has gone through that magnet because I know my principles of magnetism. And when it went through the magnet in the smaller magnet, here they are going through. There's not that many of them. So what these are magnetic flux lines, as if they are coming through the plane. We can draw those as X's or as dots, whatever. But not very many of them will be in this 1 meter squared, but more of them will be in this 1 meter squared. So I have normalized, and here's more of them here. So this is literally a more magnetic material. I can make them as dots or crosses. It depends on what direction I want to be showing. I can flip over this little plane and make it the other way. I don't care about the direction right now because I'm doing a quantity of a count in an amount of space. So this one is pretty magnetic, and I should have drawn those in blue, but this is pretty magnetic, very magnetic. And this is not very magnetic. And the reason why we normalize is because what if I actually have these bar magnets of the same material, but then this one is bigger? What if it's bigger? Of course, it's going to have more lines of flux. So magnetic flux density isn't about how many lines of flux there are. Of course, a bigger magnet is going to be a stronger magnet. Of course. So magnetic flux density is the normalized magnetic flux amount. So we normalize. Normalize is an English language word that says to look with respect to a standard. Here in our Southern Ontario culture, we tend to normalize when we go grocery shopping for cereal. Cereal happens to be a type of carbohydrate that we are familiar with eating for breakfast. It comes in boxes. And when we shop for cereal, some of the boxes are small and some of the boxes are really, really big. And then they have a price, and there's a price on this box, and there's a price on this box. We expect the bigger box to cost more, right? This has an increased cost, and this one is cost lower. But how do we know which one is a better deal? Which one is a better deal? We normalize the cost per per kilogram, or we can do the cost per volume, or cost per volume, right? Per meters cubed, which not usually, we usually do it per kilogram, which isn't really a very good comparison because the two cereals, one could be dense in mass and the other one is not dense in mass. Therefore, the price price per kilogram isn't the best uh, measure to normalize by. Maybe perhaps we should be normalizing by calories, cost per calorie. But anyway, to normalize means divide by something common so that I can compare two very different things in a fair way. So magnetic flux is just, magnetic flux density is just the magnetic flux we know, which are just counts of lines of force divided by meter squared. They are just the Webers divided by meter squared. They just look like this over here. That's easy. This is a standard SI units, Webers per meter squared. SI, System International, base units. But we have this guy named Tesla, who you might know. And this guy named Tesla was also a scientist who studied magnetism. And Tesla decided that when he's counting out these 1 times 10 to the 8 lines of flux, when he gets 1 times 10 to the 8 lines of flux in a meter squared, he's going to name that after himself and call that a Tesla. And he's also going to give it its own symbol. And that symbol is a beta. So Tesla said, I'm going to actually call it a beta with the symbol Tesla. With the unit Tesla, which is actually an SI unit, but it's not a base SI unit. I'm going to call that flux in Webers over meter squared. So now we have a new definition. It's beta. We have a new unit, it's Tesla. Did we need any of it? No, because we know what Webers are and we know what meters squared are. So magnetic flux density is the number of Webers per meter squared. If it is 1 Tesla, then it's 1 Weber per meter squared. But in general, this is our formula for magnetic flux density, which tells us how dense those lines of flux are. Very, very dense or not very dense per meter squared. So now we know a couple of things. We know, I'm just going to summarize here. If I were to write this on sort of a formula sheet, I would say beta is magnetic flux density, which is normalized magnetic flux lines per unit area. And so beta looks like magnetic flux lines, which are in Webers, over area, which is in meters squared. And that is my magnetic flux density formula. It has the units of Tesla, but the units of Tesla just break down into the standard SI units of Weber per meter squared. So don't be afraid to use Webers per meter squared instead of Teslas in general.